Next topic area we're going to discuss is ice and rain protection. And again, this one has kind of come um, after pneumatic, just like we did pneumatic, then environmental control and pressurization is ice and rain protection relies heavily on most aircraft on the pneumatic system, the bleed air as the source. There's also electric anti-ice and de-ice as well. That's going to run on the electrical system, but primarily the primary means of ice protection on transport aircraft is going to be hot air based. So ice and rain protection, it's got a few areas where we want that it focuses on. So the biggest two are kind of our lift production. Actually, these are all, I would say they're all probably pretty much the first three are going to be equally important. So lift production, we want to make sure that we don't cause the wings to not be able to do their job, and the horizontal stabilizer in that to a slightly lesser degree, but still very important. So lift production, we're going to have anti-ice as well as de-ice methods for that. Thrust production, we want to protect the engines from ice ingestion, and so we have anti-ice there. The crew needs to maintain situational awareness, visibility, and instrumentation, so things like anti-ice and anti-fog. Been quite a few aircraft that have crashed because of icing on the things like angle of attack indicators and different navigational and situational awareness devices. And then finally, passenger services, things like our water and waste system. We got to make sure things like drains and water tanks don't freeze at altitude when it's cold and things like that. So here's just kind of some areas showing those different areas that are often protected from ice and rain. So windows, window heat, windshield wipers up on the flight deck windows. The side windows really doesn't do anything. Passenger windows aren't really an important thing. It's primarily just the windshields, the front of the airplane. You can see total air temp and pitot probes, pitot tubes, as well as angle of attack indicators, so instrumentation, things in the nose area. Wings have anti-ice and nacelles to prevent ice. That's that lift and thrust protection. And then finally, there are drain masts along the bottom of the aircraft here for things like lavatory sinks and the sinks in the galley and those kind of things. Those typically drain overboard compared to the toilets, which the waste from the toilets is going to be held in holding tanks on board the aircraft to be emptied on the ground. But the hand washing water, the water overflow from the coffee makers, that kind of thing, that's all typically just drained overboard into the atmosphere. So when we're looking at ice protection, it's ice protection is generally broken down into two things. That's ice prevention, known as anti-ice, or if we're removing ice, then we call it de-ice. And then rain protection is kind of its own thing and has limited times when we apply it, because in most phases of flight, rain protection, being able to see out the windows, isn't as important as keeping instrumentation operating properly. So rain protection is primarily concerned with crew visibility during things like taxi, takeoff, and landing, but not so much in the cruise phase of flight. So when we get into ice prevention, one of the first types of ice prevention and common in areas all over the aircraft is thermal electric. So using, in the simplest form, using electricity and running through some kind of a resistive heating element, and that heats up to protect it. And so here are examples of different areas that may be anti-iced. So with thermal electric anti-ice. So pitot tubes is shown here. This is actually a pitot and static probe. But pitot-static tubes and probes, and you can, if you look closely at this, you can kind of make out that it's discolored. It's kind of got some blued areas and dark areas, and that's a result of the heat. It's normal. You see that happening, but that heat on there does cause it to kind of change color like that. Strangely enough, the total air temperature probe, which is the outside air temperature probe, those are heated to keep them from icing up, and yet they can still measure temperature. Angle of attack vanes for stall protection. windows, the drain masts for the sinks and the lavatories and galleys. Some smaller aircraft, they'll use thermoelectric for engine inlets. Turboprops often have thermoelectric boots on the leading edges of the propellers. And then some wings and stabilizers. Again, aircraft tend to use thermoelectric if they don't have pneumatic bleed air. And then there's always that caveat, the 787. The Boeing 787, again, no bleed architecture, doesn't have bleed air available. So that actually uses thermoelectric for the leading edges of the wing stabilizers and engine inlets. And that is a heated skin in those areas that's used for ice prevention. If we look at kind of how windows look, here's some cross sections of heated windows. This has the added benefit of also increasing strength. So heated windshields, which is we're going to heat primarily the outside surface of the windshield. So on both of these windshields, there's a couple, these just show a couple windshield buildups. In both cases, the outside of the windshield is on top. They have an anti-ice layer, anti-ice system, located just below the surface glass on the outside. So it's going to warm the outside, but it's not really going to warm the inside of the window so much. It's not an anti-fog. It's to prevent ice buildup on this outer layer here. And so here's our anti-ice layer here. And so it is to prevent ice buildup, but these are typically on most transport aircraft. The window heat is actually run almost all the time and not necessarily for ice prevention, but by keeping that window warmer, it makes it less brittle. So it makes it stronger in case of an impact. And so it has kind of a double advantage and it's run all the time. You can often see these, if you look through these heated windows, you can see very small wires. They even cause a little bit of, there we go, I actually have this highlighted. It can actually cause like a little bit of distortion when you look through the window, where you can kind of see the anti-ice heating elements just below the surface. It actually is there's a very strange effect when you're looking through these windows, is that you can tell, oftentimes you can tell when the anti-ice cycles on and off. It turns on, heats to a certain point, and then there are temperature sensors embedded in the glass. So when it gets up to temperature, then it shuts off the flow of current in order to prevent from overheating. And so it'll cycle on and off, and you can actually see it causes when the current turns on, you actually see a slight blurring in your view. Like it makes your eyesight almost kind of slightly blurry through the window. And then it shuts off, it goes back to being clear. That's in addition to the fact that you can often see the actual wires themselves embedded in the glass. And then, like I said, along the edge somewhere, there's going to be temperatures that are used to help control these systems. Pneumatic bleed is the most common way of providing ice protection for things like wings, tail, and engine inlets, but then air is also used for anti-fog. And so in the previous slide, I mentioned that ice protection, windshield ice protection, those heating elements are close to the surface to warm the outside, but they don't actually warm the inside to prevent fog. And so on the inside, air from the environmental control system is typically is vented and ducted on the inside of the window, just like the defroster in your car, that's used to prevent fog from forming on the inside of the flight deck windows. But the majority of pneumatic bleed air heat is used to prevent that ice buildup on the wings and on some aircraft on the tail, and then on the engine inlets, by routing hot air into those areas in order to prevent ice from forming. So, and this then has a few components. You've got heat control valves that are going to allow turn that air on and off, because again, it'll heat just like the windows cycle. The heat in these areas will cycle until the surface gets up to a certain set temperature, and then the airflow will be shut off for a period of time to allow it to cool to prevent it from overheating. And then the air is distributed inside of the inside of kind of the leading edge of the wing by something called a piccolo tube, which is a long tube with a bunch of holes. And I've got some better pictures of those here in a second. And then throughout the system, you'll have various pressure and temperature switches and sensors in order to monitor and control and provide feedback to the computers that do it, that operate it. So here's one of the shutoff valves on top. You see it's just a basic butterfly valve with a motor that can open and close it. And then on the right, here's the piccolo tube. And so what this is showing is that air is routed, comes out into the wing through this piccolo tube. And as it travels through the tube, there's little holes drilled in it, and that's inside the leading edge of the wing. And so those distribute that hot air on the inside of the wing. And then there's going to be vents that allow the air to escape out, and usually they're on the bottom of the wing. And so you'll see these little vents along the bottom of the wing, just behind the leading edge or at the rear of the leading edge material. And so that hot air can be constantly turned over in order to heat the wing. The other way that you'll see, particularly on smaller transport aircraft or turboprops, is many of them use pneumatic de-ice boots. And now we're getting into ice removal. So this is de-ice instead of anti-ice. So along the mainly in leading edges of the wings and stabilizers, you'll have your pneumatic anti-ice or de-ice boots, excuse me, not anti-ice, but de-ice. So thermal pneumatic is de-ice, is anti-ice. Anti-ice prevents the buildup. De-ice boots remove the buildup of ice. And so these can be on the horizontal, they're on the horizontal surfaces, they can be on the vertical, on the rudder or the vertical stabilizer as well, leading edges. And the way these operate is they operate in cycles. So most of the time there's actually a vacuum applied. So they do both a vacuum and pressure. So a vacuum is applied to keep them pulled down tight and smooth along the surface to allow a good airflow. But then what will happen is if the aircraft's in icing conditions, is a thin layer of ice will start to form on the surface of the leading edge and the boot. And once that has formed to over a certain period of time, then the vacuum is shut off and pressure is sent to the de-ice boot and it blows up or inflates to create kind of the scalloped appearance. And if there's any ice that has formed, it will crack it and fracture it and cause it to shed off. And so there's that de-ice, the ice is removed from the surface. And after the boots have inflated for a few seconds, then they are deflated and then they're sucked back down flat again for that process to repeat. And so the cycling of these boots is typically done automatically with some kind of a cycle timer. And the aircraft will, throughout the course of time that the boots are turned on, it will inflate and deflate them repeatedly in different zones, but making sure to allow time for ice to actually build up enough that it can fracture off. One of the risks of this is if they actually cycle too quickly, if they cycle before the ice is thick enough to fracture, they can actually push the ice up and kind of create a shell at the inflation point, and you get something called ice bridging. And then the boots will end up inflating and deflating underneath the ice and never fracture it off. So running them too often, if the cycles are too short, can actually be detrimental compared to allowing a certain amount of ice to build up so that it can be fractured off. In any of these cases, the crew needs to be able to know if icing is a concern, and so we use ice detection probes in order to do this. So here's an image of an ice detector and kind of the schematic of what's going on here. And ice detector probes are piezoelectric devices that are used to sense ice buildup through changes in frequency. And so the way they work is with this, the probe that's shown here, and kind of draw a line. The part of the probe, the skin of the airplane would be here, and the right side over here, this is what's outside the airplane. This is on the outside of the airplane. The left side is inside, And these are bolted on. So what we're seeing in the top, where we're seeing this area here, is this area shown by the right side here. And there's a little knob that kind of sticks out. It's about an inch, inch and a half long. And the driver inside of here, it's a piezoelectric driver, induces a high frequency, 40,000 hertz, 40 kilohertz frequency of vibration in this little probe right here sticking out into the airstream. And that probe is designed in such a way that it's actually got a slightly rough surface. It's not perfectly polished smooth. And so what'll happen is if the aircraft is in icing conditions, ice will start to form, and it'll form like a blob or a coating on the end of, on this little probe right here. So you get ice buildup. But when the ice buildup occurs on there, that will damp out some of that vibration, and it will change the frequency of the vibration. And then there's, in addition to the generator, the vibration generator that's putting a 40,000 cycle or 40 kilohertz vibration into the probe, there's a second pickup piezoelectric sensor that's sensing the resultant vibration. And so as ice builds up on that probe, it will slow down the vibration, it'll damp it, and so you'll get a difference, you'll get a split between what the generator is trying to vibrate it at and what the pickup side is actually experiencing. And so that is how the aircraft knows that ice is built up, is that there's a frequency change in that little probe sticking out in the airstream. And so the ice builds up, the frequency changes, and then the computer that controls these, what it'll do, these are also thermal electrically heated. They can be heated, but the heat isn't normally on. So when that probe changes frequency, it will actually heat it up to melt that ice back off and make sure it goes back to 40,000 hertz. And then it'll cycle the heat, it'll turn the heat back off again. And then if the frequency changes, then the airplane knows that it has built up, that ice is built up, and that it's in icing conditions, and it can give the crew an indication of that. And so what happens is these will sit there, and most of the time in clear conditions, the heater will be shut off. But if ice builds up, then the heater will come on and melt it off. And typically it has to go through 2 cycles like this. So it has to have ice build up, a reduction in frequency, it melts it off, and then ice build up, causes a reduction in frequency. When that does that a second time within a certain period of time, a short duration, then an indication will occur in the flight deck letting the crew know that they're in icing conditions. And then if the aircraft continues to fly in icing conditions, then the heat will continue to cycle on and off and looking for that change in vibration. It'll heat up, it'll clear the probe, it'll shut off, ice will build up, frequency will drop, it'll heat up, clear the probe, turn the heat off, frequency will drop. And it keeps doing that over and over and over again. Then it has to have a couple, then it has to have a cycle where it heats, and then the frequency doesn't drop after that. And after a certain period of time, then the ice detection system is programmed to say, okay, you're no longer in icing, and it's clear. And so it's a kind of an ingenious way of just using these high frequency vibration to sense for ice buildup. The last area, rain and fog protection. So again, these are primarily used for visibility purposes for taxi, takeoff, and landing. But during flight, the crew on these aircraft really aren't looking out the windows much. They are relying primarily on instruments for keeping the aircraft on track and flying straight and level, and then also things like TCAS, Terminal Collision Avoidance System, to be on the lookout for other aircraft, and then weather radar for that, and then air traffic control. At the altitudes and speeds, and particularly low visibility conditions like night and things like that, the view outside really is a small part of the situational awareness. And so windshield wipers shown here, these are in what's called the parked position when they're not in use. They kind of get moved off to the side so they're not sitting on the window. one that keeps them out of the pilot's line of sight. It also prevents them from sitting in one spot in the glass and scratching or damaging, wearing an area of the glass. So they park up on the metal window frame. But then they can be operated. They work just similar to your car wipers, just much more heavy duty. They have a fair amount of force that they push down on the window to overcome the fact that the plane's flying hundreds of miles an hour. But then they can be run and controlled. They have intermittent or continuous or fast or slow modes depending on the aircraft. But the big key for the maintenance side is you never want to run these across dry windows. And so when we're testing them, if somebody's in the flight deck operating them, when you have somebody on the outside of the aircraft, and usually we would just have like a spray bottle of water or some other way to keep the windshield wet while we were testing them. You also want to make sure the windshield's fairly clean before you do this, because if you get any kind of dirt or rocks or pebbles caught and run them across the window, they can scratch the windows up. Another option some aircraft have is a chemical rain repellent, kind of like the sprayer on the windshield of your car. Kind of, that's more of a window cleaner, but a rain repellent works kind of like a Rain-X type material that there's little nozzles below the window that aim the fluid up on the windshield, and those rain repellents oftentimes they have a certain amount of ice protection as well. They've got like an ice melt in them. And then they coat the window. They leave a coating on that causes water to bead off. And so that's another option. Usually aircraft have one or the other. If you have a rain repellent system, oftentimes the reservoir is somewhere in the flight deck where the crew can actually refill it during flight for longer flights if need be. And then inside, to prevent fogging, I talked about, we take warm air from the ECS system, and we have vents right along the inside of the window to prevent fogging from things like moisture from exhalation and stuff like that. So altogether, that provides enough visibility for things like takeoff, landing, and taxi phases of flight. That pretty good, but in particularly bad weather conditions, oftentimes there'll be a ground stop anyways. And so the aircraft won't be allowed to move simply because trying to maintain situational awareness is impossible. So that wraps up ice, rain, and fog protection.